Math 1314, section IC1, spring 2022, Tyler Junior College, homework 9.3 and 9.4, logarithms and their properties, video 2, logarithms. All right, if we were not in a time constraint, there would be a conversation about inverse functions and exponential functions leading up to an in-depth conversation leading up to the idea of a logarithm. I'm going to give you the short version of it. Recall that an exponential function's graph passes the horizontal line test, and hence an exponential function has an inverse. That's a lot to throw at you at once, so let's take it in bits and pieces. An exponential function, a very basic exponential function, I should say, is a function of the form some number to the x power. And more specifically, what makes a function exponential is the variable is in the exponent and in the exponent only. So as basic as they get is something like 2 to the x power. And recall that the graph of an exponential function looks something like this. This is the graph of f of x equals 2 to the x power with 4 specific points on it from left to right. When I put in -1 for the exponent, I get out 1/2. Remember, negative exponents create reciprocals. When I put in 0 for an exponent, I get 1 because anything that isn't 0 raised to the 0 power is equal to 1. The second point is easy. When I put in 1, I get out 2 to the first power, which is 2. And the last point is also easy. When I put in 2, I get out 2 to the second power, which is 4. Hence this rightmost point. Let me make that 4 a little bit better there. Hold on. Should have typed these ordered pairs, but we're already here. I also want to remind you that this graph on the right goes up forever. It's in behavior. The right hand rises, but on the left, it settles down to an asymptote. In fact, this graph has an asymptote at y equals 0. It has a horizontal asymptote at y equals 0. It's only on the left half, so it's just a half asymptote. That's a joke. All right, but this graph also passes the horizontal line test. When we talked about functions having an inverse, we said they had to be 1 to 1, which meant that the only way you could get equal outputs is if you have equal inputs. There was a visual way to check for that. Grab a horizontal line, move it up and down. And if you can only cross the graph once at a time with any horizontal line, then the graph is 1 to 1. The function is 1 to 1, and therefore the function has an inverse. So this raises a question. The question is, what function is the inverse of, and I'm going to draw the function, f of x equals 2 to the x power. Well, keep in mind that an inverse function basically undoes what a function does. So whatever this inverse function is, I know 4 things that it does based on this graph. Remember, the notation for inverse is the function with what looks like a -1 power. I wrote it larger so it's easier to see because my -1s are getting kind of skimpy there. But here's what I know about this inverse function. It should reverse everything that happened on these 4 dots on the graph. For example, the leftmost dot is -1, 1/2. I'm getting my equal signs cleaned up. The leftmost dot is -1, 1/2, which means when I put -1 into the original function, I get out 1/2. My inverse should reverse the process. My inverse should start with the 1/2 and give me back the -1. My inverse should take the 1 and give me back the 0 because my function took 0 and gave me 1. My inverse function should take in 2 and give me back 1 because my original function took in 1 and gave me back 2. And finally, my inverse function should take a 4 and give me back a 2 because my original function gave me a 2 and it took a 2 and gave me back a 4. So the question is, what is this inverse function? What is f inverse of x? Well, think about what all of these answers had to do for this particular function. This function said, give me a number and I'll raise 2 to a power and I'll give you back the answer. So if I give them the answer, what I'm really giving them is the answer to 2 to some power. So the output of f inverse of 1/2 is asking a question, what power turned the 2 into a 1/2? The function, the inverse of 1 is equal to 0 is asking the question, what power would I put on a 2 to turn it into a 1? And the answer was the 0 power. Or, excuse me, when I say f inverse of 2 is 1, the question I'm being asked is what power got put on the 2 to turn it into a 2, and the answer was a 1. And finally, when, let's see, I haven't used this color yet. When my function turned 2 into 4 and my inverse function took the 4, the question it's trying to answer is what power was put on the 2 to turn it into a 4, and the answer was a second power. So if you think about it, the reverse function is asking the question, the inverse function is asking the question, what power turned 2 into this input? What power turned 2 into 4? 2. That's right down here. What power turned 2 into 1? Excuse me. What power turned 2 into 2? A first power. What power turned 2 into 1? A 0 power. What power turned 2 into 1/2? A -1 power. So every one of these is asking the question, what power turned 2 into something? Let's clean up all those arrows and colors and everything. It's just going to be messy on the PDF. All right, so I can kind of describe what my inverse function is. The inverse of f of x equals, and I'm going to type 2 to the x power using the caret symbol. That's the pretty standard way to type left to right an exponent, but the inverse of 2 to the x power is some function that takes in a number and asks the question, what power turned 2 into that number? So for example, if we were still using the same function, f of x equals 2 to the x power, and I asked you what is, didn't want to do that, and I asked you what is f inverse of 32. Now that's asking what power turns the base into 32. Now you may not know what the answer is, but you know what the answer is supposed to do. You could just start multiplying 2's until you hit 32. Well, 2 to the third power is 2 times 2 times 2 is 8. 2 to the fourth power is 2 times 2 times 2 times 2, which is 16. 2 to the fifth power is 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times the fifth and final 2 gives me 32. So if my function was f of x equals 2 to the x power, then f inverse of 32 has to be 5, because 5 is the power that turns 2 into 32. So we kind of know what the function is asking. It's like a question. What power turns 2 into this input? And the answer to the inverse function is whatever the missing power is. But what is the name of the function that takes in a number and says, what power turned 2 into that? And the answer is defined as a logarithm. The inverse of f of x equals 2, and I'm going to draw in the x, is, I'm going to draw in the x. Actually, I'll just type it up there. Give me 1 second to throw a text box up there with a slightly smaller font. There we go. The inverse of 2 to the x power is log base 2 of x. And I'm going to put f inverse in front of that because that's what we're attempting to answer. Now, this may not answer anything. You're like, what is that thing over there? Why is it log? Why is a little 2 down there? And what does this function do? Well, I kind of already said what this function does. Log base 2 of x, and I'll throw a base 2 under there in just a second. Log base 2 of x, ask the question, what power turns 2 into x? Let me put the base 2 down there. We go. Okay, so log base 2 asks the question, what power turns 2 into x? And it is important to point out that that's how you read this. You read this expression as log base 2 of x. There has to be a base involved because you're undoing an exponential function like 2 to the x, and every exponential function is defined by its base. So there has to be some base mentioned when you're doing what's basically called a logarithm. And in fact, that thing is called a logarithm, L-O-G-A-R-I-T-H-M. Looks like it's vowel deficient at the end, but that is the way you spell it, logarithm. L-O-G-A-R-I-T-H-M. But a logarithm is simply a power that turns a base into a given value. I think that's worth typing. Let's put it back in 36-point font and answer the question, what is a logarithm? A logarithm is the power that turns some base into some value. So in order to give the answer to a logarithm, you have to have two numbers already given to you. What is the base and what value are you trying to achieve? So for example, let's say I asked you, what is log base 3 of 81? Log base 3 of 81. This is asking a question. I can't stress this enough. I'm going to sound like a broken record. You're going to hear it a ton. All a logarithm does is ask a question. The question this one is asking is what power turns 3 into 81? Now, it's not important to know the answer right away, but it is critical to know what the answer is supposed to do. I am looking for a number that does this. 3 to what power is equal to 81? Now, if you're lucky, you can just keep multiplying until you run across it. If you have a calculator, you can just start multiplying 3s and then stop and count how many you had when you hit the correct number. Now, I'm going to use a calculator on here so that I can just do a screen share with you. And we're just going to start multiplying 3s until we hit 81. Just keep count. 3 times 3 equals, that's 2 3s I've multiplied so far. That's just 9. Times 3, here comes a third 3, equals, that's 27. Here comes a fourth 3, times a fourth 3 is 81. It took 4 3s multiplied to get 81. That means that 3 to the 4th power is 81, which means the answer to the question I just asked is 4 is the power that turns 3 into 81. So a logarithm is a question. What power turns the base into the argument? Now, I just introduced a new word to you, so let's get the vocabulary out there while I'm thinking about it. This number down here is called the base. It's called the base because it's also the base in the exponential problem. But the number on the inside, there are some mathematicians and teachers that do not call it this. They ought to, because that's its name. The number inside is called the argument. Argument is actually the generic word for the input of a function, but I use it specifically when we talk about logarithms, because when we define what a logarithm is, I want to use the words base and argument. So that's all of what logarithm is. It's a power that turns some base into some argument. Let's try one more. And at some point, we're actually going to define what this is. Okay, let's get everything ready here. I've been filling with font sizes and colors. I'm going to post 3 log problems. We'll start with log base 4 of 16. This one is easy. We do log base 5 of 1. This one's also pretty easy. And log base 7 of 1 over 49. This one you have to think about a little bit. But I want you to think about what question each one of these is asking in terms of powers and bases. For example, what question is the first one answering? Log base asking, log base 4 of 16. Log base 4 of 16 is asking what power turns 4 into 16. What question is log base 5 of 1 asking? It's asking what power turns the base 5 into the argument 1. And what question is log base 7 of 1 over 49 asking? It's asking what power turns the base 7 into the argument 1 over 49. Again, you don't have to know what the answer is, but you darn sure need to know what the question is, because once you pose the question, you can think about what number makes this work. Do you know the answer to the first one, log base 4 of 16? What power would you put on a 4 to get a 16? Well, I think most of us know that 4 to the second power is 16. So the answer to the question, hold on. The answer to the question, what power turns 4 into 16, is 2, which means the answer to log base 4 of 16 is 2. A logarithm is just asking what's the missing power. Go to the second one. What power turns 5 into 1? In other words, what power, hold on, I'm going to write the question mark last. What power would I put on the 5 to get an answer of 1? Well, if you remember your exponent rules, anything to the 0 power is equal to 1, which means that the answer to what power turns 5 into 1 is 0, which means the answer to log base 5 of 1 is 0. What about the last one? What power turns 7 into 1 over 49? Now, if it were just a 49, the answer would be 2. 7 to the second power, 7 squared is 49. But it's 1 over 49. What types of powers create reciprocal answers? Negative powers. 7 to the negative 2 power is equal to 1 over 49, because 7 to the negative 2 power means 7 to the 1 over 7 to the second power, which of course is 1 over 49. So what power turns 7 into 1 over 49? Negative 2. So what is log base 7 of 1 over 49? Negative 2. That's all a logarithm is. A logarithm is a power that turns the base into the argument. That sounds good. We should write that. So let's do that. A logarithm is the power, and I'm going to say the power because for a given problem, it is a unique power. Remember, it has to be because our exponential graph was 1-to-1. It passed a horizontal line test. We're just doing the exponential graph backwards. A logarithm is the power that turns a base into an argument. Remember, the argument is just the input of the logarithm problem. Let's see if we can write something generic here, because this is kind of critical. There's no kind of to it. It's very critical. If I write a problem like log base B, B is good for base, I wonder what letter I should use for argument. How about A? If I say log base B of A is equal to some number, we'll just call it X. Well, why do you get to be the answer to a logarithm? Well, what question is this problem asking? I know it's got B's and A's, but what question is it asking? We'll put it back in red. The question this is asking is what power turns the base B into the argument A? So whatever the answer to this is, has to be the power that turns the base into the argument. But what was underneath the first blue rectangle? Do you remember? An X. So guess what should be underneath this little blue rectangle? An X. These statements are equivalent. These statements are equivalent. I'll put a double-headed arrow between them, meaning that this happens only when this happens. That is the definition of logarithms, and in the next video, we'll talk about going back and forth between these two expressions with a few more examples.